Dr. O here, and welcome to Chapter 4, where we take a dive into the world of molecules and compounds. Now, when we previously put together the Lewis structures, they were very simple, and I gave you some real simple rules to follow, but as we move forward and we start to do more complex structures, we actually need some more complex rules to help guide us. So rule number 1 is that you need to count the total number of valence electrons and get a count of how many electrons you need to place. And we're going to do this, and you'll see why that becomes important. The next thing you do is you need to lay out the skeletal structure. And in this case, you want to put the one that is least electronegative, the element that is least electronegative, in the center. Unless, of course, it's hydrogen, in which case hydrogen will always be on an end because it can only bond with one thing. So how do you determine if you're dealing with the most electronegative and least electronegative elements? Well, across a row, the elements increase in electronegativity. So you're going to see where they fall within that row. We're not going to deal with a great number of varied elements. So that rule about the row tends to work. Number 3, place a bonding electron pair between the connecting atoms to demonstrate that those are being shared. Number 4, complete the octets of the atoms that are on the outside, the terminal atoms. So you give all of them an octet. And then number 5, then you start placing any leftover electrons in the central atoms so that they form octets. And if you don't have enough electrons to place on the central atoms, then you can actually move electrons from the terminal atoms because they can share more than one pair. So this is the rules for dealing with Lewis structures. So let's try our hand at a more complex structure. Let's take a look at carbon tetrachloride, and we can take a peek at carbon. We know it has 4 valence electrons, and then chlorine comes from column 7A, which means it's going to have 7 electrons that it's going to bring to the table. But here's the deal. We have 1 carbon, it'll bring 4 electrons, but we have 4 chlorines, and each one is going to bring 7. So chlorine will contribute 28 electrons. And that 28 plus the 4 electrons from carbon means that we have 32 electrons total that we need to find homes for. Now, when we look at carbon and we look at chlorine, we're going to find that carbon is the least electronegative. It's less electronegative than chlorine. So we'll put the carbon in the center and we'll place the 4 chlorines around it. And then the next thing that we need to do is we need to place electron pairs between bonding atoms. So we're going to place 8 of our 32 right there. And then we're going to start dropping in the other electrons around all those chlorines. So we have 8 that we placed. There's 9 and 10, 11 and 12, 13, 14, 15, 16, 17, 18. Yep, I'm going to do all 32. 19, 20, 21, 22, 23, 24, 25, 26, 27, 28, 29, 30, 31, and 32. So that's worked out rather nicely. Now, if we wanted to do the lines, we could replace the electron pairs that are shared with a single line. So we could bring all of those lone pair electrons around the chlorine, but instead of showing the dots between the carbon and the chlorines, we could just draw lines because each line represents 2 electrons. And that's how you would do a Lewis structure for carbon tetrachloride. Now, we just drew a Lewis structure for a molecule that had a single bond. And a single bond is a shared pair of electrons, which is what we saw. It's 2 electrons being shared between atoms. And these lines between the chlorine and the carbon are conveying that this is a single bond. It's just 1 pair of electrons that are being shared. So why am I telling you about single bonds? Well, it's because we can also have a double bond. So what do you think a double bond is? If a single is a pair, a single pair, then a double bond would be 2 shared pairs of electrons, a total of 4 electrons that get shared between atoms. And the way that we would convey this with a Lewis structure would be with 2 2 lines between the atoms that are sharing those 4 electrons. And if we have a double, might we also have a triple? And indeed, that's the case. What do you think a triple bond is? That would be 3 shared pair of electrons, a total of 6 electrons shared between 2 atoms. And we would draw that with a Lewis structure with 3 lines representing those 3 pairs, or those 6 electrons. Okay, so just a moment ago we saw that carbon dioxide has a couple of double bonds. So let's prove to ourselves that that's true. So we know that each carbon is going to bring 4 valence electrons, and oxygen is a 6A element, which means it has 6 valence electrons. And if we count up our electrons, each carbon will contribute 4, each oxygen will contribute 6, and we have 2 of them for a total of 12 electrons. We add all of that, and we need placement for 16 electrons. All right, so the next thing we need to do is we need to place the least electronegative element of our 3 elements in some sort of a skeletal structure, and carbon is going to be in the center of our 2 oxygens because it is less electronegative than either one of those oxygens. And now we need to place a couple of electrons between carbon and oxygen, and I know those are placed funny, but there's a reason for that. And now we start populating the oxygens. The oxygens are on the end of this molecule. So we have 2 4 placed, and there's 5 6 and 7 8 and 9 10 11 12 13 14 15 16. Okay, so we placed all 16. Let's take a look at what we have. Well, this oxygen and that oxygen both have 8 electrons, so they've satisfied that whole octet rule. But what about carbon? Carbon only has 4 electrons. It does not have a full octet, and it needs one. So what are we going to do? Well, we can grab a couple of electrons, let's say from the oxygen on the left, and they can share with carbon. And we can grab a couple of electrons from the oxygen on the right, and they can share with the carbon. Now let's recount and see what we have. We still have octets with both oxygens. Even though they're sharing 4 electrons with carbon, they still have an octet. And what about carbon? Now carbon has an octet too. Well, that works out just dandy. And what do we notice? How many electrons are being shared between carbon and the oxygen on the left? 4. What do 4 electrons represent? 2 bonding pairs. And the same thing is true between carbon and the oxygen on the right. So we could redraw this structure and put in a couple of lines here and a couple of lines there. And this is how carbon is doubly bonded to oxygen. This is what Lewis predicts, and it works. Hallelujah. Let's take a look at a nitrogen atom. 2 nitrogens bound together. Can you guess where we're going to go with this one? Yeah, we're probably headed towards a triple bond, but let's just see. So nitrogen is a 5A element. It has 5 electrons in its valence shell, which means that we're going to have a total of 10 electrons that we need to place between the 2 nitrogens that make up this molecule. So we start with 2 in the center, and then we're going to populate starting on the nitrogen on the left. So we have 2, 3, 4, 5, 6, 7, 8, 9, 10. All right, we already see we have a problem, don't we? Nitrogen on the left has 8 electrons. Nitrogen on the right only has 4. So we can share a couple of electrons, and now the nitrogen on the left still has 8 and nitrogen on the right has 6. That's better, but it also needs 8 electrons. So let's grab a couple of more of these lone pair electrons and share them with the nitrogen on the right. Now let's see what we have. We have, well, now in this case we have 6 electrons being shared between them, and each one has its lone pair. So now each nitrogen has a total of 8 electrons, which satisfies the octet rule. And if we look at the number of electrons between them, that's 6 electrons. That's 3 bonding pairs. And when we redraw that, each pair gets a line, and we have a triple bond. And Lewis predicts that this is how this works. And indeed, that's how it works. So let's take a look at this molecule and see if we can't apply Lewis's rules and see if this molecule exists in nature. Because that's what Lewis was trying to predict. Do certain molecules exist in nature? All right, so the first thing we need to do is count our valence electrons. And carbon brings 4, and oxygen brings 1, and hydrogen brings 1, oxygen brings 6. And if we do the math, we can just spell out everything. There's 3 of those hydrogens, so there will be 3 electrons. And then oxygen has 6, and when we add that up, we're going to have 13 electrons. Now, I'm going to tell you already, my alarm bells are going off because we really shouldn't have an odd number of electrons. So I'm already suspect at this point. All right, but we've done step number 1. Step number 2 is to figure out who is least electronegative and is it going to go in the middle. So let's look, and that's going to be carbon. So let's drop carbon in the middle, and we have 3 hydrogens. Let's place those, and let's put this oxygen right here. Now the next thing we need to do is place bonding electrons between the atoms that are meeting. And that gives us 8 of our 13. So now let's populate oxygen with the remainder. So we have 8, 9, 10, 11, 12, and 13. All right, when we draw it like this, what we see is that carbon has the octet, but oxygen doesn't. So we can see that we already have a problem and that this structure doesn't work. So let's try it again. How about if we were to have carbon bond with just a couple of hydrogens and then it bound to this oxygen, but then instead of putting that third hydrogen on the carbon, we put it out here. Let's just try this. Well, we could do a couple here, we could do a couple there, we could do a couple there. There's 6, 7, 8, 9, 10, 11, 12, and 13. So we're still stuck with this issue that we don't have enough electrons to form an octet. We don't have a way to share pairs. And so essentially we're not satisfying the octet rule. So Lewis basically predicts that this won't work either. So by following Lewis's rules, we've basically determined that there's not a simple way for this particular molecule to exist in nature, at least like this. So Lewis tells us that when we work with his methods, we can accurately predict that neither one of these arrangements of these atoms will work in this way. But we can change and make some predictions that, given some other circumstances, that these might work. Now, we're kind of going beyond the lecture at this point, but I want to prove the point that how powerful Lewis's little method was. Let's look at the structure at the bottom, and also because I know somebody's going to look it up and say, well, it would work if you had just done this. So I'm just going to head you off and go there for you. Let's look at the molecule at the bottom. Now, carbon really wants to have an extra electron. So if we were to drop just an extra electron in there under carbon, the problem with doing that is that now carbon would bear this negative charge. And carbon is not a real electronegative atom. So it doesn't have the ability to sustain that extra electron. It just doesn't have the ability to hug it and keep it and make it be stable. So that's not going to work. But if instead of just dropping an electron, we also dropped in a proton and a neutron, i.e. a hydrogen atom, then this would work. This molecule does exist in nature, and we call it methanol. And Lewis predicts that this is what we would need to make this structure work, and he's right. What about the upper structure? What could we do with this one? Well, we could follow the same pattern and say we could complete the octet for oxygen by dropping in an electron. Now here's the deal with oxygen. Oxygen is the more electronegative element, which means that it can grab an electron from somebody and kind of hang on to it. So it has the ability to bear that charge. And the way we would convey that to the reader is that we would have to put that little negative sign in the superscript. I know I didn't do that down below, but I was trying to make a point down below of why that didn't work. We would put that negative in the superscript, and we would put this parentheses around it and say this entire structure is now an ion. So Lewis predicts that each one of these can exist if we make a couple of changes, and in fact they both do exist. So how do we go about naming molecules? Well, let's take a look at how we name formula units first, a review of naming ionic compounds. So here we have sodium ion and chloride. Remember, it gets the "ide" ending. Get rid of the ion, smush those two together, and this is how we would name sodium chloride. This is the process that you go through for naming an ionic substance. So how does it differ when it comes to naming a molecular substance? So now that we did this quick review of naming ionic formula units, how do we actually name a molecule? Well, we have to name the first element in our formula, and we'll have to name a second element as well. But this time, we're going to include the number of each atom in the formula, and that's important because different combinations, different numbers of atoms can make up different sorts of molecules. So what are these number prefixes that we have to include? Well, here they are right here. So if we have one atom, it gets a prefix of mono. If there's two, we get di. Three, there's tri, and so on and so forth. So let's actually use this information and see if we can't name something. So we probably already know the name of this, but let's go through our new protocol that we just learned and see how these rules get applied. All right, so the first element is carbon, and the second element gets a name, and it is oxygen. Now, do we leave it oxygen? No, we don't. Do we change the first name? No, we don't. So let's start with that. So carbon is going to remain carbon, but the second name is going to change. We're going to actually call it oxide. Now, what does that look like? That looks like how we name the second element in an ionic formula unit. And indeed, that is. We're going to follow that same pattern. So in these simple two-atom molecules, we're going to turn the second atom into an ide. Even though it's not a negatively charged atom, it's going to be an ide. All right, now we have to apply these numbers over here. So how many carbons do we have? We have one carbon. And how many oxygens do we have? Well, if we look at that little subscript 2, that means we have two of them, so we're going to put a di there. Now there's actually a fourth rule, and this fourth rule is this. If your mono is in the first position, you drop it. So we have mono in the first position, mono carbon dioxide, which means we can drop that mono, and the name of CO2 is carbon dioxide. And that's pretty much how that works. Let's take a look at another one. How about this one? Well, our first element is carbon. Our second element is chlorine. Carbon remains carbon, but what do we change chlorine to? It becomes chloride, right? How many carbons do we have? One, so it's mono. How many chlorides do we have? Well, we can see there's a 4 in that little subscript, so if we go over to our chart, we can see that 4 is tetra. Now we have mono in the first position, which means we can get rid of it, and the name of this molecule becomes carbon tetrachloride. Now it just wouldn't be chemistry unless we had some weird exceptions, so I'm going to introduce you to some exceptions, and then I'll tell you how I grade them. Let's take a look at this character. We have one carbon, and we have one oxygen. Now we know carbon stays carbon, and we know that oxygen becomes oxide. And we have one carbon, and we have one oxygen. And we can drop the mono from carbon. But let's look at this mono in front of oxide. Now, if you didn't know any better and you were to read that, you might actually read that carbon monoxide. Now, we don't want it to sound like monoxide. So what we end up doing is we eliminate one of those O's and we make it monoxide. So there is a rule that says that when you have more than one repeating vowel, under certain circumstances, you get rid of it. And monoxide is one of those circumstances. I think we would get rid of those two O's because the sound of the O can change when you have two O's together. The sound of a single O can be ah, as in cot, or O as in poke when it ends in E. And you can also have two different sounds of a double O sound. You can have like an oo sound, as in can't think of a word, pool, or you can have an sound, as in sort of a cook, like a sound. I guess not a it's an. So I guess to keep it simplified, they just get rid of that second O because it can completely change the sound of the two O's that should be pronounced individually. Let's take a look at this one. So we have nitrogen and we have iodine. Nitrogen stays nitrogen. Iodine becomes iodide. We have one nitrogen. We have three iodide. And we're going to get rid of that mono. But in the case of triiodide, we're actually going to keep it, because tri tells us about three and iodide tells us about the element. All right, so why am I introducing you to these two crazy rules? Well, because there's a lot of variation. Do you hang on to an O before an A? Do you hang on to an A before an O? I mean, there's all of these possibilities. So when you see it in a quiz, when you see it on an exam, give it your best shot. Basically, if you're dealing with the molecule, you need to have those numeric prefixes. That's really what I want to see. Whether you double the O or you eliminate it to one, whether you hang on to both of those I's or you get rid of one of them, I don't really care. As long as you demonstrate to me that you have three iodines and you know that you need a TRI somewhere in there, you get credit. But anyway, I wanted to show you that the rules there's a reason for them, but we don't need to know them. We just need to know that when we're dealing with molecules, we got to have some sort of a numeric prefix there, even if we do it just a little bit wrong. All right, that's that. All right, let's try our hand at our newfound knowledge. So we have these two molecules, these two formulas, I should say. And if you were to set about naming them, what would be the very first thing you would need to do? The very first thing you need to do is determine what type of molecule or structure you're talking about. And how do we do that? Well, you look at what's in the first position. What is aluminum? It's a metal. What is nitrogen? A nonmetal. What do you get when you put a metal with a nonmetal? Because chlorine is a nonmetal. When you have a metal and a nonmetal, you're dealing with an ionic compound, which means you have to follow the naming rules for ionic compounds. When you have a nonmetal and a nonmetal, then you've got a molecule, and you have to follow the naming rules for molecules. So when you're looking on the exam or the quiz, you want to make sure you look at what's in that first position first in order to figure out which set of naming rules you're going to employ. So in order to name these two, let's look at the first one. So we know that Al is aluminum and Cl is chlorine. Aluminum stays aluminum and chlorine becomes chloride. Now what do? We don't do anything because aluminum chloride is the name of this formula right here. It's ionic, so we don't have to include those numbers. But what about over here? Well, we have nitrogen and we have chlorine, and we know that nitrogen stays nitrogen, chlorine becomes chloride. And now we have to put in some numbers, right? So we have one nitrogen, we have three chlorines, and we're going to drop that mono. And here's the name of our compound, nitrogen trichloride. And that's it. So when you're looking at these, and you'll have to be able to tease them apart, because I won't say name these ions and then name these molecules. They will be in there together. Ask yourself what's in the first position, and that will dictate the naming rules. So how do we come up with the mass of a formula? Well, you have to first of all know the mass of the elements that make it up. So let's look up the mass for carbon. Well, we know it comes in at 12.01 atomic mass units. We could do the same thing for oxygen, 16 atomic mass units. And what if we had a formula that looked like this? Carbon monoxide. Carbon monoxide. Well, it has one carbon and it has one oxygen. And we could just simply add those two masses together. And the formula mass for carbon monoxide ends up being 28.01 atomic mass units. What about carbon dioxide? Well, we have one carbon, but instead of one oxygen, we now have two. So we're going to have to double those oxygens, and that changes the mass. The mass of carbon dioxide is 44.01 atomic mass units. Anything hard here? Hopefully not. So the way that we come up with formula mass is that you take the mass of each element in the formula and then you add it all together. That's it. Okay, now we're going to start our discussion on molar mass. So what is molar mass? Well, it has a little something to do with this guy right here. Amedeo Avogadro was an Italian count. He was royalty, but he was also a scientist, and he was the real deal. You see, back when he was alive and a little bit before, as well as many years after, royalty was very interested in the sciences, and a lot of them weren't very smart in and of themselves, so they would actually pay smart guys to come hang out in the castle and make discoveries, and then the royal person would put their name on it. But not Avogadro. Avogadro was the real deal. And his claim to fame was that he was trying to figure out, I'm going to say this, but it's not really true. He was trying to figure out how you weigh gas. Now, he knew that you couldn't weigh gas, but there had to be some way that we could define it, because he understood that gas had mass and that it had some weight to it. He understood that. But he also knew that you couldn't round it up and put it on a scale. So he was coming at it from a different way. And what he discovered was based upon this. He was able to isolate 12 grams of the carbon-12 isotope. And when he did that, he found that it had a correlation to this number, that in 12 grams of carbon-12 atoms, you had 602 sextillion atoms. Now, the calculations that led him to this discovery are phenomenal. I've seen it. So I know this guy was a genius. So this number is now called Avogadro's number because of its significance. And we've also, more modernly, have come to correlate this with the mole. So we could say that there's a relationship between 12 grams of carbon-12 and 1 mole of carbon atoms. Now, why is that important? Why is correlation between any three of these pieces of information important? Because basically what Avogadro gave us was a relationship between two different types of units. And when we use two different types of units, then that allows us to interconvert between those types of units. So even though I only have the gram and the mole here, because that's what is relative to our discussion with molar mass, we could also create a relationship between grams and the number of atoms in that many grams, or we could create a relationship between like a, I don't know, 2 moles and the number of atoms in it. So we could create a relationship between grams and number of atoms in grams, or even the number of atoms in a mole or the number of atoms in a gram. So all three of these are interrelated, and it was Avogadro that paved the way. All right, so that's a little bit about that. Now, when we look at a periodic table, the number that's in the square with the symbol for the element is known as the atomic mass, and it comes in the units known as atomic mass units. So, for example, if we were to look at carbon, we would see 12.01 in the square, and we would pull that right out of the square knowing that what we were dealing with was 12.01 atomic mass units. Well, how does this correlate with molar mass? Well, molar mass, as I just stated below, says that this is the amount of mass in 1 mole of a particular type of atom. And the correlation between molar mass is that we can take the value that we see in that square for and that would originally come off the periodic table in atomic mass units and simply replace atomic mass units with grams per mole. So for in the example of carbon, where previously it was 12.01 atomic mass units, if we wanted to talk about its molar mass, we could say 12.01 grams per mole. And when you see it written this way, now we're into the world of conversion factors, and we're going to be doing a lot of that. So this is the prelude to tell you we're getting into the mathy part of the lecture. So I'm going to show you my method, and I repeat this for these types of problems. You're going to see me go through these steps every single time that I work a problem. And I know that you're going to develop your own, but when you're first starting out, if you're unsure, you will have the sound of my voice and all of my animations to guide you until it becomes second nature. So you're going to see that. Just want to point it out. All right, here we have a problem. And it's asking us how many grams of carbon is in 0.9 moles of carbon. Well, as I read this problem, what I know is that I've been given the number of moles and I'm being asked to convert that into the number of grams. And the question I need to ask myself is, what do I know that allows me to establish a relationship between the number of moles and the number of grams? Well, that would be molar mass, specifically carbon's molar mass. Now, how do we come up with molar mass? You go to the periodic table, you look at that little number that we know is on the periodic table in atomic mass units, but we're going to drop it into a fraction that looks like this, 12.01 grams per mole. And I have intentionally put in that grams of carbon over mole of carbon. I've done that for a reason, and that's because I want you to understand how I'm getting the information that I'm getting. So I'm leaving nothing to chance here. It's a little overkill, but I'm leaving nothing to chance. All right, I have to go back and read my problem, and it's giving me the number of moles and it's asking me to find grams. So ultimately, whatever I end up in needs to be in grams because I'm interconverting units. So I like to start with what I'm given, which is 0.900 moles of carbon, and I'm going to use my conversion factor that I have written right here, which is 12.01 grams of carbon over 1 mole of carbon. Now, by setting it up this way, I have a repeating unit. Technically, that first number, 0.900 moles, is over a 1, which means that it is in the numerator. And the mole in my molar mass is in the denominator, so I have a repeating term and I can get rid of repeating terms. Now I've gotten rid of the units of mole and the only unit I have left is gram, which is good because I'm being asked how many grams. At this point I can simply do the math. And my math would be multiplying 0.9 times 12.01, and technically there is a 1 underneath 12.01, but when you divide anything by 1, it is that value. So doing the math, I end up with 10.8 grams of carbon. These are the steps for using molar mass to convert from moles into grams. So let's take a look at another one. So this problem is asking us how many moles of lithium is in 15.6 grams of lithium. So as I look at my solutions map, I can say I've been given grams and I want to know moles. And what do I know that correlates grams and moles? Well, that would be lithium's molar mass. That's the only thing we're talking about here is lithium. Now I'm going to point you to this little bit. Now we're being given the grams and we're being asked to find the moles. Now why am I pointing that out? Because this is going to make a difference in how we write our molar mass. And this is a rule that you need to be mindful of once you start creating your own conversion factors. So we're being given, in this scenario, we're being given the grams, but we need to find the moles. So when you write your conversion factor for molar mass, or actually for anything, but in this case molar mass, you want to make sure that your conversion factor has the units that you seek on top. And in this scenario, the units that we seek are going to be the mole. So when we write the molar mass for lithium, we're not going to say 6.94 grams of lithium over 1 mole of lithium. We're going to flip it upside down and we're going to say 1 mole of lithium over 6.94 grams. The 6.94 comes straight out of the periodic table, but instead of putting it in the top, I've turned it upside down, and you can do that with conversion factors because no matter how you write it, it means the same thing. When we say it this way, the way it's written here, we're saying that for every mole of lithium, you have 6.94 grams of lithium. If we flipped it the other way, we could say that for every 6.94 grams of lithium, that's equal to 1 mole of lithium. So these two values are the same, they're just in different units, which means that you can write them with one on top and the other one on the bottom, or you can switch it around. You can use it as you need to, and in this case, we need for the moles to be on top in order for everything to work out right. Okay, so to set this problem up, I actually kind of like to work it out when I put my solutions map out because it helps me have just that moment of double check and clarity. So I'm in grams, I want to be in moles, the units I seek need to go on top, so I'm going to put my moles on top. Now I've created my conversion factor, and I don't have to think come the next stage, which is setting the problem up in the equation. So I like to start with what I'm given, which is 15.6 grams of lithium. And now I'm going to use my predetermined conversion factor. I'm going to drop that right in. And now I can get rid of repeating terms. So I have a grams of lithium on the bottom, grams of lithium on the top. The only units left standing are moles of lithium, which is great because I'm being asked how many moles. And now I would do the math. In this case, we're going to multiply 15.6 times 1, and we're going to divide it by 6.94. And when we do that, we end up with 2.25 moles of lithium. So let's add another layer to this. Now this question is asking us how many atoms of lithium are in 15.6 grams of lithium. Now just a minute ago we were just dealing with moles and grams, which is great because we could just deal with molar mass. Now we're asking about atoms. So we have grams, we're given grams, and we're being asked about atoms, which is basically the number of particles. They're asking us how many number of particles. Now, do we know anything that directly correlates the number of grams with the number of particles? Well, no, we don't. But what we do know is that we can go from grams to moles. And then there is a relationship between moles and the number of particles. What gets us out of grams and into moles? Well, that would be lithium's molar mass. And which of the units is going to be on top on our conversion factor? Well, we're given grams, but we want moles as our first step. So we're going to write that conversion factor with the moles on top. So we're just inverting the grams per mole and writing it kind of upside down. Now, what sort of relationship do we know that will allow us to create a relationship between the number of moles and the number of particles? Well, it's this relationship right here. We know that 1 mole of lithium is equal to 6.02 times 10 to the 23rd number of lithium atoms. And if we're going to use these two pieces of information to create a conversion factor, which piece of information needs to go on top? Well, it's going to be Avogadro's number over moles, because we're going to end up with the number of atoms. So that's how we've done that. Okay, so we've created two conversion factors that are going to allow us to go from grams to the number of particles. To set up our equation, I always like to start with what we're given. So we've been given 15.6 grams of lithium. We're going to drop in our first conversion factor. And we can even get rid of repeating terms at this point. So we have grams of lithium on the bottom and on the top. Now we can drop in our second conversion factor. And we can even get rid of some repeating terms here. We can get rid of moles of lithium and moles of lithium. And technically the only units, and I'm doing air quotes, units, that are left are the number of lithium atoms. I don't write out lithium atoms because it's too long, but I do put that little hashtag meaning number in there so that you understand what I'm doing. When students don't label this part, they get confused because they don't know what Avogadro's number is actually telling them. It's telling you the number of particles, whether it's atoms or whether it's molecules. It could be either one. So that's why I like to put that hashtag lithium there. All right, now at this point we can do the math. We can multiply 15.6 times 1 times 6.02 times 10 to the 23rd, and then we can divide all of that by 6.94. And when we do, we get a number that looks like this. 1.35 times 10 to the 24th number of lithium atoms in 15.6 grams of lithium. Now I'll tell you, before I get off this slide, I'll tell you, we have gone from grams to particles, and you're going to need to be able to go from particles to grams. Now if we go from particles to grams, what are you going to do with your conversion factors? They're going to go the other way. So your grams will be on top, moles will be on the bottom for your molar mass. And then the relationship between the mole and Avogadro's number, the mole will be on top and Avogadro's number will be on the bottom. Now if you don't trust me, you can always write that out. You can run this problem in reverse and figure it out. I don't include one here because I didn't want this lecture to be any longer than it needed to be. But you need to be able to run the solutions map forward and backwards. And if you can do that, then you can do any portion of this, whether it's solving grams to moles, moles to grams, or number of particles to moles, or moles to number of particles. You've got it nailed. All right, another thing that we need to deal with is mass percent. Now, formulas tell us a lot of things. Formulas can tell us about the type of compound we're dealing with. You know, what's in that first position, a metal or a nonmetal. That tells us if it's ionic or molecular. It can predict the structure and the way that the elements are coming together to form that molecule, or even form the lattice structure for our ionic compound. It'll allow us to calculate the mass of a molecule, the formula mass. And we can even calculate mass percent of an element as a result of the formula. And that's what we're going to be doing in these next few slides. So here's the formula for coming up with the mass percent of an element within a formula. It's really not that hard. So you would take the mass of 1 mole of the element that you were interested in figuring out the mass percent of. And then you would take the mass of 1 mole of that compound and divide it into the mass of 1 mole of your element, and then you multiply all that by 100. So what is that going to look like? So let's calculate the mass percent of something. So let's say that we have water here. Water is going to be made up of 2 hydrogens and an oxygen, and we can figure out the mass that the hydrogen is contributing comes in at 2.016 grams, because there's 2 of them. And each one is contributing 1.008 grams per mole of water. And oxygen is going to contribute 16 grams of mass per mole. Now, water overall has a mass of 18.016. So if we look at our formula, we would say that the mass percent of oxygen is the mass of oxygen over the mass of water times 100. And when we do this math, we end up with oxygen coming in as a percentage of the mass of water, 88.8%. So that's how you would calculate the mass of an element in a formula, using the formula of that element, the mass formula of it. So now that we figured out how to determine the mass percent of an element in a compound, we can actually use that information as a conversion factor. So there's nothing like a demonstration to help us figure that out. So let's do this problem here. So chlorine is 58.64% of the mass of a freon molecule, which is what a couple of chlorines, a couple of fluorines, and a carbon make up. And we're being asked how much chlorine, basically what mass of chlorine is going to be in 575 grams of freon. Well, that may seem like a hard problem, but follow me, if you will. From the previous slide, we learned that this is the formula for discovering the mass percent, but we don't need to do that because it's given to us in this problem right here. We know what the mass percent of chlorine is in a molecule of freon. But what does that mean? What does that tell us? Well, among the things that it could tell us is that if we had 100 grams of freon, we could know that 58.64 grams of it are going to be chlorine. You see what I did there? I just plucked out 100 grams because I know that for every 100%, 58.64% is going to be chlorine. And instead of using percentage, I put the grams to it. Now I've created a relationship between grams of freon and grams of chlorine. And I can create a conversion factor. Actually, I can create 2. I can create a conversion factor with the chlorine on top and the freon on the bottom, or I can do it the other way with the freon on top and the chlorine on bottom. It doesn't really matter because it means the same thing. It means that for every 58.64 grams of chlorine, given the ratio that I have, I should have 100 grams of freon. Or if I have 100 grams of freon, I know that 58.64 grams of it are going to be chlorine. So which of these conversion factors am I going to use? Well, I go back to my problem and I reread it. And I can see that I've been given grams of Freon, and I want to basically know how much chlorine, how many grams of chlorine. So I'm going to set this up starting with what I'm given, which is 575 grams of Freon. And I am going to use the conversion factor with the grams of chlorine on top because that's where I want to go to. So I'm going to drop that in. And I can get rid of repeating units, which are grams of Freon. I'm left with grams of chlorine, and now I do the math. I'm going to multiply 575 times 58.64 grams of chlorine, and then I'm going to divide it by 100, and I end up with 337 grams of chlorine. So for every 575 grams of fluorine, I know that 337 grams of it are going to be chlorine. And that, my friends, is how you would use your mass percent as a conversion factor. Now, believe it or not, we can use formulas as conversion factors too. And there's nothing like working a problem to help us figure things out, so let's work this one. How many grams of hydrogen are in 125 grams of water? Well, what do we know? Well, we know this, for example. So what is this telling us? What is this formula for water telling us? Well, literally what it's telling us is that we need 2 hydrogen atoms and an oxygen atom in order to make up a molecule of water. Now, that's not very much. What if we wanted to make up more than just a molecule? Well, I don't know. Let's say we took 2 dozen hydrogen atoms and 1 dozen oxygen atoms. We could create a dozen water molecules. And that's certainly more than 1, but it really isn't very much. And we're not bakers. We're chemists. Do chemists have a counting unit? Why, yes, we do. It's the mole. So we could apply the mole to these symbols, to this formula, just like we applied the dozen. And we could say 2 moles of hydrogen atoms is equal to 1 mole of oxygen atom, and as a result of putting them together, we would have 1 mole of water molecules. And once we do that, now we have something meaningful that we can work with, particularly given that what we're dealing with are grams. You see where I'm going here? Moles and grams, grams and moles. All right, so what this is telling us then is that for 2 moles of hydrogen, it takes 1 mole of oxygen, and we can create 1 mole of water molecules. So there is a relationship between 2 moles of hydrogen and 1 mole of water molecules. There's a relationship between 1 mole of oxygen and 1 mole of water molecules. And there's a relationship between 2 moles of hydrogen and 1 moles of oxygen in this scenario. So that's what this is telling us, is we have all these relationships. What relationship are we interested in? We're interested in the relationship between water and hydrogen. So when we look at the ratio using the moles, what we're going to be interested in using are the moles of hydrogen and the moles of water when we get to that. Now, I've already kind of led you into knowing what else we're going to use because we're using the units grams and moles. So we're going to be working in molar mass somewhere. So let me ask you this. What do you think our solutions map is going to look like? Well, we're going to start with our 125 grams of water. And if we're going to use molar mass, we can get out of grams of water and into moles of water. Now, what else on this page can we relate moles of water to? We can relate moles of water to moles of hydrogen, 2 of them, from the line just above this. And we don't want to be left with moles of hydrogen because our question is actually asking us about grams of hydrogen. So we're going to then use the molar mass of hydrogen to get us into whatever the grams of hydrogen are. Now at each one of these arrows, we should be able to come up with a conversion factor. To go from grams of water to moles of water, we need to use the molar mass of water. And the units that we seek are going to go on top, which means that our moles of water are going to be over our grams of water. Now, when we go from moles of water to moles of hydrogen, we're going to use the information that says 1 mole of water has a relationship to 2 moles of hydrogen. Who's going to go on top? Our 2 moles of hydrogen are going to go on top of 1 mole of water. And then we're going to use the molar mass of hydrogen to get us out of moles of hydrogen and into grams of hydrogen. And what kind of relationship do we know about that? Well, we know that it's 1.008 grams of hydrogen has a relationship with 1 mole of hydrogen. That's the molar mass. So by working this little solutions map and coming up with our 3 different conversion factors using the information that we know about molar mass and the information that we now know that we can use and apply moles to a formula, we have created basically everything we need to solve this problem. So when I set up my problems, I like to start with what I'm given, and what I'm given is 125 grams of water. I'm going to drop in my first conversion factor. I'm going to drop in my second conversion factor. I'm going to drop in my third conversion factor. And you know me, I like to get rid of those repeating terms. So I have grams of water on the bottom and grams of water on top. I have moles of water on the bottom, moles of water on top. I have mole of hydrogen on the bottom, mole of hydrogen on top. And I'm leaving all the numbers standing because all I'm getting rid of when I do that cross out are the units. Now I can do the math. I can take 125, multiply it by 1, multiply it by 2, multiply it by 1.008, and I can divide it by 18.016. And when I do all of that, I end up with 14.0 grams of hydrogen. So this kind of really puts it together how we can take molar mass and our understanding of formulas and put it all together and actually use it as a rather powerful tool when trying to figure out what we're dealing with as far as different amounts of stuff. So that's that. I hope that makes it clear for you. Now, earlier in this lecture, I talked about how our early forefathers in chemistry were using empirical formula, and they were degrading substances, and from that they were able to combine the two and actually give us the molecular formula of a substance. So we're going to do some of that right now. So let's say that we had water and we were able to decompose it into 0.58 grams of hydrogen and 6.86 grams of oxygen. Could we determine the formula for water? Well, the answer is yes. So how are we going to do that? Well, we can think of formulas as being in units of moles, as we just saw from the previous example. So let's see if we can make some conversions here. Let's say that we have this 0.58 grams of hydrogen. Can we get it out of grams of hydrogen and into moles of hydrogen? Yes, we can, and we would use molar mass. And the units we seek would be moles, so it's going to go on top. And we get rid of our repeating units of grams, and we do the math, and we could convert that 0.58 grams of hydrogen into 0.85 moles of hydrogen. Let's do the same thing with water. We're going to multiply it by its molar mass, get rid of repeating terms, do the math, and when it comes to water, we have 0.429 moles of oxygen. I think I said water, but we're talking about oxygen. So what are we going to do with these two pieces of information? Well, also, just a moment ago, we said that when you're looking at a formula, the amounts that you see written in the subscript, whether it's the implied 1 or a 2, as in H2O, is a molar value. It's the number of moles. Well, we have some moles here. We have 0.85 moles of hydrogen, and we have 0.429 moles of hydrogen. So we're going to put those in our formula, like this, and like that. Well, that looks kind of crazy, doesn't it? It's because we don't see that. And in fact, it was John Dalton that told us early in this term that when you write a formula, you have to write it using whole numbers. You can't have these fractions. So how are we going to get rid of this fraction? Well, it's a little bit of a math gymnastics, and we're going to take the smallest value, which is a 0.429, and we're going to divide both of these molar values by 0.429. And when we do that, the obvious thing that's going to happen is that oxygen has a subscript that's going to go to 1, and hydrogen's subscript is going to go to 1.9. Now we still don't want to have a decimal there. We want it to be a whole number. So we're going to round this up because it ends up being something like 1.997, which is real close to 2. So our formula becomes H2O. So there you go. So if we were able to decompose some water into what we see up here, we could actually kind of back it back in by converting those mass values into mole values and plugging them into or convert into a formula, and then doing this mathematical gymnastics and come up with a formula. And that's what some of the stuff that our early forefathers were doing in order to give us the formulas that we have now. So what were the steps that I used in order to create my formula? Well, I took the mass of the elements that I got through the degradation process, and I converted them to moles using molar mass. That was step number 1. And then I took those mole values and I put it into the formula. So I dropped them into those subscripts. And then in the case of my experimental data, I divided the subscripts by the smallest value in order to get those whole number values. So when I divide by the smallest value, that means that one is always going to go to 1 and the other one may have to be tweaked a little bit through rounding. If you have a fractional subscript, you might be able to use the chart that's included in the book. And if we look at what this chart's trying to do for us, it's saying that if you have a fractional subscript of 0.2, you can multiply it by 5. And that would take that to 1. You can multiply 0.25 by 4, and that'll take you to 1. You can multiply 0.4 times 5, and that'll take you to 2. So what this is basically trying to say is that when you have something on this chart, we have a number that you can multiply that number by, those subscripts by, in order to easily reduce it. So let's do an example using the chart. So let's say that we had element A in relation with element B, and we have 0.25. We can multiply that by 4 and the other one by 4 as well. What's good for the goose, good for the gander. And A would have a subscript of 1 and B would now have a subscript of 4, and our formula would be AB4. What about a compound that looks like this? Can we use the chart? We sure could. Multiply them both by 5. Our A goes to 4, our B goes to 10, and our formula becomes A4B10. Now, would you want to reduce this further? Well, it depends. If we're talking about a molecule, then we're going to need every A, all 4 of them, and all 10 of those B's to have the right recipe for this compound. But what if we're talking about an ionic substance? Well, then we could reduce that 4 and that 10 down to a 2 and a 5. Because remember, when we're talking about ionic substances, those are just ratios, and you want to reduce the ratio down to the lowest common denominator. But if you're talking about the molecule, you need them all there. Since we don't know what A and B are, we're just going to leave it. All right, what about this one, where we have A 0.429 and B 0.85? Do either one of these numbers show up on the chart? Nope, which is why we took the smallest number and divided both of those values by it, and then got the numbers that we did and had to do a little bit more tweaking, and we came up with a formula that looks like this. So that's how you use your data in order to create a formula. Now, also early on, we talked about empirical formulas. And there is a way that we can utilize empirical formulas to come up with molecular formulas. So you might remember this chart, this particular slide. We talked about how glucose and ribose both had the same empirical formula, but they have different molecular formulas, which means they have different formula masses. So if we can correlate formula mass back to empirical formula, we can probably come up with the molecular formula. So let's do that. All right, so let's use the empirical formula to create a molecular formula, or deduce our molecular formula. And let's work a problem to do that. So we have a substance that has a mass of 80.2 grams per mole. We don't know what it is. We don't know what its formula is. We know it's a sugar, but we don't know which one. And we have the empirical formula for sugars below. Can we figure out the molecular formula? Yeah, we can. Now, what we're given is 80.2 grams per mole. Do you think maybe we should figure out the molar mass of our empirical formula? Yeah, that might be a good idea. So let's do that. So we have 1 carbon, 2 hydrogens, and an oxygen. And when we add all of those up, we have a molar mass of our empirical formula of 30.03 grams per mole. If we divide that into our mysterious sugar substance, we take our 80.2 grams per mole, divide it by 30.03 grams per mole, we get a value of 6. So what is that telling us? That's telling us that we have 6 of our empirical formulas going into 6 of whatever the formula is for our substance. So we could take that 6 and say that it's basically our N. And what we're looking at here is glucose. This is the formula for glucose, where we have 6 carbons, 12 hydrogens, and 6 oxygens. So our empirical formula goes in, the molar mass of our empirical formula goes into our substance 6 times. It has a relationship of 6 to 1, which means our N is 6. And we can come up with our formula. What if our substance had a mass of 150.15 grams per mole? Well, if we divided it by the molar mass of our empirical formula, we have a value of 5. 5 would be the N, and our formula would then be 5 carbons, 10 hydrogens, 5 oxygens, and that would be the formula for ribose. So this is the sort of stuff that our forefathers were doing. They would decompose the compounds down into their constituent elements. So like if we were to do this from the very beginning, we would take our sugar and we would decompose it down into a mole of carbon, 2 moles of hydrogen, and a mole of oxygen. We'd be able to capture all of that and figure it out. And then come up with this pseudo formula that's our empirical formula, and then take the mass of the substance that we started with, and then figure out the molar mass of our pseudo formula, our empirical formula, and then back it in and figure out that there was a 6 to 1 ratio, and then from that calculate our molecular formula. This was the sort of stuff that they were doing before they actually had high-tech equipment and could figure it out some other way. So this kind of brings everything together that we looked at as we made it through this chapter. We looked at what the formulas are telling us and how to apply numbers and how to use that in order to get some additional information. And with that, I think we are done with this chapter.